Okay, this is project test 3, video number 2, problems 11 to 20. A carnival game allows the player a choice of simultaneously rolling 2, 4, 6, 8, or 10 fair dice. Each dice has 6 faces numbered 1 through 6. After the player rolls the dice, the numbers that appear on the faces that land up are recorded. The player wins if the greatest number recorded is a 1 or a 2. How many dice should the player choose to roll to maximize the chance of winning? So let's go ahead and make a sample space. So we can get a 1, 2, 3, 4, 5, or 6. That's what can happen. Now, to win, we have to roll only those numbers. Well, that's 1, 2 out of 6. So 2 out of 6 wins, which is 1/3. Okay, so we want to win 1/3, and the question is, we only can win 1/3 of the time. But how many dice should we roll? What's going to give us the best chance? And we have, how many dice are there? 2, 4, 6, 8, or 10. So we can go 1/3 squared, or 1/3 to the 4th, or 1/3 to the 6th, or 1/3 to the 8th, or 1/3 to the 9th. Well, pretty quickly, we're going to recognize that our best chance of winning is with only 2 dice. So 1 divided by 3, and if we just square that, 1 divided by 3 squared, and our chance of winning is 0.111. If I go 1 divided by 3 and do it with anything else, raise it to the 4th power, our probability decreases. 1 divided by 3 raised to the 1, or divided by 3, enter, raised to the 6th power, and it just gets smaller and smaller and smaller. And so our best chance, we have a 1 in 9 chance, which is our best chance if we roll 2 dice, right? All we did was say, hey, you know what? The probability of winning is 1/3, and it's more likely if I only roll 2 dice, I'm best to win. All right, that's my best chance of winning. Okay, number 12. A school is having a contest in which students guess the number of candies in a jar. The student whose guess is the closest to the correct number of candies in a jar wins a prize. The number of candies guessed by male and female students is shown in the back-to-back stem plot. Okay, and please note that they gave us a key, so 6 line 4 is 64. All right, which of the following is true about the statement of guesses? The distribution of guesses for male students is skewed to the left, the distribution for female guesses is skewed to the right. Whenever they do the back-to-back, it gets a little bit confusing for people. So here's my suggestion. Let's go ahead and over here we'll do the male, and we'll do them first just because they're on the left-hand side. And we're starting off 6, 7, 8, all the way to 14. Well, we are going to be shaped with just a few over here and a lot over here. This is stretched to the left, so this is skewed left. So the males are skewed left. When we look at the females, we have 6, 7, and 12. And we have 1, 2, 3 here, 1 here, several more here. And so ours is also stretched to the left, which means it's skewed left. So both distributions are skewed left. And so this one said skewed left and one skewed right. That's incorrect. The distribution of guesses for male students is skewed to the right. Nope, they're skewed to the left. The distribution of guesses for male and females are both skewed to the right. Nope, they're both skewed to the left. The distribution of guesses for male and female students are both skewed to the left. Yes, and clearly they were not symmetric. So B is our best answer. E wasn't even a possibility. Okay, as neither were symmetric. The manager of a car company will select a random sample of customers to create a 90% confidence interval to estimate the proportion of its customers on the who have children. Of the following, which is the smallest sample size that will result in a margin of error of no more than 6 percentage points? So we're going to write down our confidence interval formula, which is p hat plus or minus z star p hat q hat n. And please remember, this part right here equals the margin of error. And they're telling us our margin of error is 6 percentage points, so 0.06. We need to calculate Z star, and they want to do a 90% confidence interval. So we're going to go second vars, inverse norm, area, parenthesis, 1 minus 0.90, close parenthesis, divided by 2. And since this is Z, that we know that the mean is going to be 0 and the standard deviation is 1. And we're going to go ahead and make this positive when we're done. So we end up with 1.645. We know we're looking for N, so we can go ahead and write that in. And did they have an estimate for P hat? And the answer is they didn't have an estimate for P hat. So we always have to use the worst case when they don't provide one, which is 0.50. All right, I'm going to divide both sides by 1.645. This crosses out, and this part becomes, when I multiply those, they become 0.25. So we have the square root of 0.25 over n equals 0.06 divided by 1.645. If I square everything, the radical comes off, and I have 0.25 over n equals 0.06 over 1.645. So let's do this work. 0.06 divided by 1.645. And I'm going to go ahead and square that. And then I'm going to take 0.25 and divide it by what we just calculated. 0.25 divided by what we just calculated. And I get 187.91. 187.91. So n has to be greater than that because I need it to be a whole number. So in this case, n will have to be 188 or larger. So 200 is the first value that's larger than the 188 that I needed. So 13 will be D. Okay, 13 will be D in this one. All right. Next problem. Number 14. Which of the following statements must be true about the data sets A and B in the histogram above? Well, real quickly, be very careful about these. This value, we know that we because this is symmetric, we think the mean and median are going to be somewhere in here. In the end, the problem is they're somewhere in there. They could be as low as 30 or as high as 40. They're somewhere in that range. We don't know exactly where they are. And that's going to play into this problem. So which must be true, not which might be true. It might be true. They could be the same. Matter of fact, this one and this one might have the same means, but we don't know that. We just know that the mean is between 30 and 40, and the mean is between 30 and 40. Don't know where in there. So the mean of data set A is equal to the mean. Well, this one could be right here at 30. This one could be all the way up at 40. So no, we don't know. It doesn't have to be that. We just know it's in that interval. The same thing can be said about the median. We know the median is somewhere in there, but we don't know where in there. And so it could be any range within those 10 integers. The range of the set data. Well, once again, we're stuck with that problem. This could be up at 19. This would be right here at 50. This could be all the way at 10 and all the way to 60. So because we don't know where in those bins, and these bins are called these bars or bins, we don't know where the value is. We don't know the answer. The standard deviation of set A is less than the standard deviation of set B. That's false, because the more data we have close to the center, the more the data is closer to the center, more data closer to the center, smaller standard deviation. So this will have a smaller standard deviation. This will have a larger. Matter of fact, the worst case for standard deviation, well, we'll come back to that in just a second. So this is actually false. This is not even a possibility. But the standard deviation of A is greater than the standard deviation of B. That's true. We have more data away from the mean. This one has more data close to the mean. So close to the mean, small standard deviation, away from the mean, large standard deviation. Now, so this is E, but there's a couple reasons for this. First off, just from a conceptual standpoint, let's look at the formula. The formula for standard deviation is pretty ugly, but x minus mu squared over n. So basically, I'm subtracting individual values from the mean. So the farther they are from the mean, the bigger my standard deviation. The closer they are to the mean, the smaller my standard deviation. Well, this one has more that are close, so it's going to have a smaller standard deviation. Pictorially, it looks like this. If this were my histogram, this would be a standard deviation of 0, because every data point was exactly the same. This would be my smallest standard deviation. As soon as my standard deviation looks like what I like to call goalpost, like this, where my mean is in the center, this is going to have the largest. So this will have the largest of all standard deviations. This will have the smallest of standard deviations. Matter of fact, if these were all the same value, x minus mu, they'd have a standard deviation of 0. They'd also have a variance of 0 as well. All right, number 15. A box of 10 tags numbered 1 through 10 with a different number on each tag. A second box contains 8 tags, numbers 20 through 27, with a different number on each tag. One tag is drawn at random from each box. What is the expected value of the sum of the two selected tags? Well, first off, let's make this simple. What do we expect on this first one? Well, we're going to expect the average. All right, we always expect the average. And probably the easiest thing to do would be to go to stat edit and enter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into it. And then go stat calc, one variable statistics. My list was L1, so second one. And I get an average of 5.5. So drawing from the box 1, my expected value is the average, which happens to be 5.5. Box 2, my expected value is also going to be the average of that box. And I've already entered those in the stat edit right here in L2. So I'm going to go stat calc, one variable statistics, and I'm going to go second 2. And I end up getting an average of 23.5. So on average, I would expect to get a 23.5. And you're like, well, that's not even a real possibility because it's a whole number. I know, but that's what I would expect to get. If I did it over and over again, I would expect this average to be 5.5, and I'd expect this average to be 23.5. So doing it repeatedly, this is what I would expect to happen. But they're saying, hey, I'm going to draw from 2 boxes. What is my combined expected value? Well, remember, we can add means directly. We can add expected values directly. So 5.5 plus 23.5 equals 29, and our answer is E. So drawing from the 2 boxes, I would expect to draw a 29. Now think about this. I could have drawn a 27 and I could have drawn a 10. So it could have been as high as 37, or it could have been as low as 1 plus 20 is 21. So any one of the values between 21 and 37 were possible, but really I'm expecting the average from this box plus the average from this box, which equals to 29. Okay, number 16. A pollster is interested in comparing the proportions of women and men in a particular town who are in favor of a ban on fireworks within town borders. The pollster plans to test the hypothesis that the proportion of women in favor of the ban is different from the proportion of men in the ban. There are 4,673 women and 4,502 men who live in the town. From a simple random sample of 40 women in the town, the pollster finds, so we have a simple random sample, that's good. Of 40 women in the town, the pollster finds that 38 of them favor the ban. From the independent sample, so we have a second sample of men. So we have two independent samples. This is a good thing. All right, so we need two independent samples. We have that. They need to be random. That we do. That's great. And the next big thing is we need NP and NQ greater than 10 for both of them. Well, when I look at the women, we have 38 women for NP, but our NQ is 40 minus 38, because we surveyed 40 women, I believe. And so that means 40 minus 38 is 2. So we don't have an NQ greater than 10. So consequently, this is not going to work out. This is just looking at the women's side of things. Because the samples are from normal populations, the two population z-test would be valid. Remember, has to be NP and NQ must be greater than 10. Didn't happen. That's how we check our normality. Otherwise, this is a binomial. Because the sample size is greater than 30, that works for an X bar for averages, but we're working with proportions. So that's not true because we're working with proportions. Because the number who favored the ban is greater than 10 in both groups, and it's like, no, it's not. You have to satisfy the other condition, those who are opposed to the ban. Because the relative size of the population of samples, NP, so basically they're trying to say here is, you know what, we had 40 divided by 0.1 is 400. That's definitely less than 4,500. We're good there, etc. So we're not too big. Our sample size isn't too big. It's less than 10%. And so we satisfy that condition, but we didn't satisfy this condition. We did not satisfy NP and NQ because our sample size was not large enough. All right, number 17. Employees at a large company can earn monthly bonuses. The distribution of monthly bonuses earned by all employees last year has a mean of 2.3. So they're telling us the mean is 2.3. They tell me the standard deviation is 1.3. And the reason I know that you're like, well, wait a second, why did you use that as opposed to sample? Because they said by all. So consequently, I have the entire population. Let Z represents a standard normal distribution. If X bar represents the mean of monthly bonuses earned last year for a simple random sample of 40, which of the following is calculations will give the approximate probability that X bar is less than 2. So we want the probability that X bar is less than 2 for a sample of 40, or N equal to 40. So that's our formula is Z equals X bar minus mu standard deviation divided by the square root of N. So the probability that Z is less than 2 minus 2.3 over 1.3 divided by the square root of 40. Well, it just turns out that our first answer is the correct one. So 17 is A. Number 18, the p-value of a one-sided t-test is 0.10. If the test had been two-sided, what would have been the probability? This is a really nice problem. Going from one-sided to two-sided is easy. One side to two side, double the p. So we're going from one-sided to two-sided, we're going to 0.10 times 2 is 0.20, and that's my answer. So that's very easy. On the other hand, going from two-sided to one-sided isn't as easy, all right? Because if we had a two-sided, let's just say we had the 20%. That means I have 0.10 in this tail and 0.10 in this tail. All right. If my alternative hypothesis, if HA had been a greater than, and it's like, oh, okay, greater than this value, well, then you're like, okay, yeah, it's 0.10, no problem, it's half. But if HA had been this way, then you're facing it down that way. And so consequently, when it's going from two tail to one tail, depends on the direction. So this is true for two tail to one tail. One tail to two tail, you can just double. One tail to two tail, you can double. For two tail to one tail, it depends on the direction of the hypothesis. A scatter plot of student heights in inches versus a corresponding arm span in inches is shown below. One of the points is labeled A, all right? And they say, if the point A is removed, which of the following statements would be true? And they start asking, the slope of the regression line is unchanged, the correlation increases. So first off, let's go ahead and draw with it A being in there, where do I think that regression line is going to be? And I don't know for sure, but I'm just going to make a guess. I'm going to say if we include A, that's my best guess. All right. Now, A is pulling it down this way. So if I remove A, what's going to happen? Well, if I remove A, I'm going to go, oh, it's going to shift up a little bit. So my line's going to shift a little bit. And so I'm going to get this line or something that maybe looks a little more like this. Actually, it's probably even more so. It's probably even going to be more like this yellow line that I'm about to draw. Probably more like the yellow line that I just drew. Now, if I did that, what we notice is with the red line, I had a lot of things, a lot of long distance away. The farther I am away from the line, the less correlation. So as points move away from the line, or the bigger my residuals, the smaller my correlation. So greater residuals, smaller correlation. And remember, residuals are the errors. How far are we from the line? How far are we from predicted? So we get rid of A, our correlation should increases. So correlation increases, I like that. Correlation decreases, that's false, so that gets rid of this. Correlation increases, that's good. Correlation decreases, that's bad. So this, all right, so these are possibility. So the ones with correlation increases are the ones that are most likely to have the case. But what also happened to my slope? Well, my slope rotated up. So that means because it turned this way, it got larger. My Y perspective got bigger. So my slope increased. So it did not remain unchanged. All right. And here it says the slope of the regression line decreased. No, it didn't decrease, it increased. So C is my best answer here. And then on number 20, let X be the random variable whose values are the number of dots that appear on the uppermost face when a fair die is rolled. The possible values are 1, 2, 3, 4, 5, or 6. So we're rolling a dice, and if we roll a dice, this is what we can get. The mean is 7/2. In other words, the expected value when you roll a dice, believe it or not, is a 3.5. Even though it doesn't occur on the dice, that's the average of what you expect. And we get a variance of 35/12. Now be real careful. So the variance is 35/12, and the standard deviation would be the square root of 35/12. And I know math people don't want it looking like that, but that's what we're going to go with. All right, so what is the standard deviation of y? Well, and we're rolling two dice. Oh, it says first minus second. And by the way, if I'm rolling two dice, I can subtract the expected values. But when it comes to standard deviations, I have to square them so that they become variances, then sum them. So I can do this. All right, because that's what this squared. So I'm just going to plug this in. And I have 35/12 plus 35/12. And that, in fact, is my answer. Please remember, we never subtract. Okay, we never subtract. Okay. By the way, if they had asked for the variance instead of the standard deviation, this would be the variance, but they asked for the standard deviation. They asked for the standard deviation. All right, that concludes this video. Thank you.